So, a liquid is heated so that after 20 seconds of heating, its temperature T is 25 degrees Celsius. After 50 seconds of heating, the temperature is 37 degrees Celsius. Okay, the temperature of the liquid at time T can be modeled by T equals AT plus B, where T is the time in seconds after the start of heating. Using this model, one of the equations can be formed. One of the equations that can be formed is 20A plus B equals 25. As you can see from the model that they created, that they substituted in after 20 seconds, which is represented by lowercase t. The temperature is 25 degrees Celsius, which is capital T. So A and B are your variables that you're trying to create a second equation for, and then of course find the values of. This problem of the day is an example of what concept? A system of equation. And so that's exactly what you have to do. You have to use the model to write down a second equation. Okay? And what you give, Anna, what you give for the second equation?
I said 50A plus B equals 37.
Very good, because 50 is the time and 37 is the temperature. So of course, to find the value of A and B, you either have to use substitution or elimination. Which route did you all go? And what variable did you eliminate? B, by turning one of the B equations to a negative, right? I'm going to go ahead and use that 20A plus B equals 25 to turn negative, because I had to rewrite it anyway. And so when I canceled out, that gave me 30A is equal to what number? Or did I mess up someone? 12. So you guys got it? Okay. And then you divide both sides by A, and A is equal to what? Sorry. Divide both sides by 30, and A is equal to what? 2 over 5. And then to find the value of B, you take one of those and plug it in. Find B, right? I'm going to use the equation that they already gave us instead of the one that I created. And if I do it this way, 20 times 2/5 is equal to what? 8. Don't forget the trick of, 5 goes into 24 times 4 times 2 is 8. 8 plus B equals 25, so B is equal to what? 17. Okay? And so it says to use the model to predict the temperature of the liquid 60 seconds after the start of heating. Which model? This one right up here. Okay? Because we do now know that the value of A is 2/5. We are looking for the temperature after the liquid is 60 seconds. So we're going to plug that in for lowercase t and capital, and then lowercase b is 17. How many times does 5 go into 60? 12 times. What's 12 times 2? And 24 plus 17 is 41. 41 what? And don't forget your units. Pretty simple. Question 2 from an old IB exam. Okay? The way that IB exams are set up is that, your easier questions they start at number 1 and then they slowly get harder as you go through. Okay? So, question. And so today we're talking about functions, notation, and more. You guys are going to learn how to find composition of functions, inverse of functions, domain and range of functions, whether or not you're even dealing with a function, all things that you have done at some point in time already. So, a relation is a set of ordered pairs, okay? A relation is a set of ordered pairs. And a function is a relation in which no two different ordered pairs have the same x-coordinate, okay? You've dealt with functions before, okay? Vertical line test was a way to determine whether a relation was a function when you were given the graph. Okay? So vertical line test, does that sound familiar? Okay? And a function, it can't have no two x values can have the same y value. That's what made something a function versus not a function. Okay? It hasn't changed from one class to the next. It's still the same. Okay? Sometimes you'll be given a set of ordered pairs, maybe in the graph, asking whether or not something is or is not a function. and you use your knowledge of that to answer the question and go from there. Function notation. You guys already know about the f of x notation, which you see right here. Okay? You guys know this. You've seen this before. But this is new. This notation right here. This is new. That too means f of x equals. Okay? It basically stands for the function f such that x is converted into whatever follows the arrow. So really and truly, this is the same thing as saying f of x equals. Okay? That notation is interchangeably used, so you want to make sure that, when you see this, you're not like, oh my god, what is that? No, it's just f of x. Okay? And then from there, you can do several different things, evaluate functions, find composite functions, etc., etc. So, on your desks, because this is not worthy of your notes, go ahead and find A, B, and C on your desk for if f of x is equal to 3x minus x squared plus 2 for each one of those values. Leah, f of 0 is what? 2. That's also known as what? When you plug 0 in for x and you find that value, that's also known as the what, Zach? When you plug in 0 for x into a function, you're actually finding the what? The y-intercept. Very good. F of 3, Maylene, is what? 2. Okay. And then f of negative 3 is what, Brady? Negative 16. Simple enough, right? Yes. Let's move forward. Okay. What about from a graph, though? Do you guys know how to do this from a graph? How to evaluate a function from a graph? Yes or no? It's okay to say no. No. Okay, thank you. All right. First off, f of x is equal to y. Okay? So you have a graph of a function shown on the side, and you're asked to find f of 2 and f of 3, and then also find the value of x such that f of x is equal to 4. If f of x equals y, then this notation right here is saying find the y value when x is 2. That's all it's asking for. So along the graph, you say, okay, well, when x is 2, what's the y value on the actual function of that graph? What's that y value? And that's your answer. That's how you use a graph to evaluate a function. Okay? So f of 2 just means when x is 2, what is the y value? Okay? So here f of 3 would be when x is 3, what's the y value? So you go to where 3 is, and then you see where exactly 3 would be along your function, and that answer would be the y value when x is 3. This one is saying find the x value such that f of x is equal to 4. So where y is 4, what's the x value? Because it's actually defined the value of x. So here's positive 4. Here's where it is on the curve. So you need the corresponding x value, which is, and that is how you evaluate it from an actual graph. Does that make sense? Just make sure that you don't mix them up. It's very common for students to mix them up. Okay? On your desk, let's do these. All these are function notation, dealing with the functions. All right, so when you plug in x plus 4 into every x that you see, you want to make sure that you do what? Here? You FOIL, so then that gives you x squared plus, combine like terms? 8x plus, awesome. This becomes wonderful, and then you have a minus 1 at the end. What do you do to the 2? Distribute, and can I combine like terms at the same time? Awesome, so this becomes 2x squared plus 19x plus, wonderful, and that's your answer for part A. You do a similar process with B. Be very careful since it's a minus x this time around. Similar process, FOIL, distribute, combine like terms. What did you get for your final answer for B? Okay, I heard the plus 13. What was the B term? Wonderful. And then this one with the negative. When you square a negative, what happens? So then you should have gotten a 2x squared minus 3x, because a positive times a negative is a negative minus 1. Yes?
Yeah.
Question?
So when it says simplest form, you don't factor it.
No.
Okay.
You just you combine all your like terms. So basically, once you plug in, you cannot leave it like this. You actually have to FOIL, combine like terms, and then get to a point where basically every term is not like something else. But when you factor, you start going a step further beyond simplifying. Good question. Okay. Domain and range. You've been doing domain and range for a while. Domain corresponds to a set of values along your horizontal axis. Okay? Usually it's X, but depending on the type of problem, it could be T, it could be W. It just really depends on the problem itself. Okay? Especially if it's an application problem, you want to make sure that it corresponds to your horizontal axis. Range, of course, is your set of values for which the variable on the vertical axis can take. So normally it's your Y's. But again, depending on the application problem, it could be capital T, could be I, could be different variables. It just depends. And domain and range can be written in two different ways, two different notations. Do you remember what they are from your last class? Set builder. What's the other one called? Set builder notation and start with I. Not inequality. It is IN, but it's not inequality. And the other one is what? Interval notation. Okay, these are the two different ways that you can represent domain and range. IB, if they are going to provide the domain for you, it is going to be in set notation. Okay, set involves inequalities, it involves commas, and it involves the notation that has the curly bracket with the x value such that, etc., etc. Does that look familiar? Okay. Now the one thing that I think is separate from like Algebra 2 and like a pre-calc class to IB is that they're under the assumption that all the numbers that you're dealing with are real numbers. You remember at the end you used to have to put x as the element of all real numbers? Maybe. You don't have to do that here. You just say exactly what the domain is. So if the domain is greater than 0, then it'll just be x is greater than 0, and then that would be it. My right curly bracket is always worse than my left, so I apologize, but you can make sure it looks like a curly bracket and not a 3 or any other type of symbol. Okay, but that is set builder notation. X for domain, and of course, what for range? Your Y. Okay? Now, the one question I do have for you is that if it's all real numbers, like negative infinity to positive infinity, how do you represent that? If you're listening, I kind of said it. There was a symbol that went here before you had the R. Anybody remember that? It was an E. This is how you would write all real numbers. Not just for range, but for domain as well, is the E and then the R. R does have like, it's like a double bar for that vertical part, and it is an E there. Okay, but it stands for Y is the element of all real numbers. That's how you can represent something like negative infinity to infinity. So that's set builder notation with the curly brackets, the inequalities, and that format. Okay? Interval notation was the one with the infinity symbol, parentheses, and square brackets. Unions, when you have multiple pieces of your domain. Does it sound familiar? Okay? So let's say that the domain was from like -2 to 5, and -2 was included, but 5 wasn't. So from -2 to 5, you use the square bracket if it is included. 5 if it's not included. The parentheses if it's not included. Negative infinity to infinity. Infinities always have the parentheses parentheses around them because it's not a defined number. Familiar? And anytime you have multiple pieces, you included the union. I'm just making up these different examples here so you can see the types of notations that are used with each one. Curly brackets with set, parentheses and square brackets with interval, infinities with interval, element of all real numbers, never infinities, and inequalities with set. Okay? Let's look at an example. I'll pull this from one of the application problems. Okay? I think this represented like a parking lot, how much you were charged depending on how long you stayed in a parking lot. Okay? Along your horizontal axis, you had your time in hours, and along your y-axis, you had your charge in pounds. Okay? What would be the domain here for this particular problem? What would be the domain? Say again. So our domain, so it sounds like you're giving to me an interval notation from 0 to 24. What would I need around the 0? A parenthesis, and around the 24, a square bracket. And the reason why it's all the values that are in between 0 and 24 is because, remember, just because there's a break here and it's undefined up here, it still is defined at that particular value, whatever it is, whether it's 1 or 1.5 or something like that. Okay? So even though there's breaks, if it's defined at the x value on one, but now on the other, it's still defined and it still exists. Okay? And it goes all the way up to 24. How would I write this in set notation? Such that this is where you would write greater than 0 but less than 24. That's written as a compound inequality. How would you write that as a compound inequality? Remember, set notation involves the inequalities, and since we're going from 0 to 24, 0 is not included, hence there's only less than. 24 is included, that's why there's the equals. Are you remembering this? Yes. Okay. The range, however, you notice how there's breaks in your y values? It's either going to be 5, 9, 11, 14, 18, 22, 28, something like that roughly. Okay? Since it's an actual set of numbers, it's not like a range between 0 and 30. You can never write in interval notation. Okay? Anytime it's individual numbers, it's always written in set notation. Okay? And if anything, it's actually easier. All you do is literally list out the y values. Okay? So, first y value would be what, 5. The next one, the one after that, the one after that, say 14. The one after that, the one after that, and the last one. You would just list them out. No need to put any type of notation, like an X such that or a Y such that. You literally just list them out. Okay? Those cannot be written in interval notation. Questions? This is a harder example. A lot of times they're just continuous functions. Okay, they have a starting point, ending point, maybe they go on and on forever. So I want you to do these. Okay? I want you to write A, B, and C in interval and set notation on your desk. So sometimes, and it really kind of depends on like your personal preference. It's not going to ask you to write it in a particular way. I already told you that IB does do set notation. Okay. However, if you ever ask to write the domain or range, they're not going to say it has to be in set builder or it has to be an interval. You just choose whichever one's more comfortable for you. And the mark scheme is always going to be the set notation way, but they're not going to penalize you if you do it one way or the other. Okay? So and that's why I had you do A, B, and C in set and also in interval. So the domain in interval notation would be what, Vegas? What would the domain for A be? In interval, yes.
So, bracket.
Bracket.
-1.
-1.
Comma infinity parentheses.
Very good. And then the range in interval would be what, Kaylee?
Bracket, -30 to infinity.
Very good. Okay, so that would be an interval notation. Did you guys get that? Okay. What about in set notation, Samuel? What about in set for the domain? The set of such that. That's
-1.
okay. Is there a shorter way I can write that? No, not x is less than infinity. Like anything on a number line, we got -1. It's defined and it's everything that's to infinity, right? So using another inequality, how can I represent everything that's this way of -1? Besides doing it as a compound, because in set you don't use it. You don't use infinities. So we can't use infinities. But greater than? Or is it -1 included? Greater than or equal to -1. Okay? Amy, what about the range? How do I write it in the set? Say again. Very good. And it's just like that. Yes?
Does it matter the way we write it?
So did you do -3 is less than or equal to y? That's fine. But no infinities in set notation. Okay? No infinities. It's either greater than the number or less than the number. Alright? Shannon, give me B in interval notation.
It would be parentheses, -infinity, comma 2, bracket.
Careful. You sure you gave me the domain? Remember, domains are your x's, and pretty much you gave me just that part. But doesn't it keep going after that?
Oh, so it would be -infinity to infinity.
There you go.
Oh, that's what it is.
Mm-hmm. What Shannon actually gave me was the what? That first time around. What she gave me? She gave me the range, which she said was -infinity to 2 with the bracket. Because the lowest it goes is -infinity, but the highest it goes is not 2. 1. Like I caught it as I was talking, I was like, wait a minute, that point is the y value. So variation. So if it has those arrows, it means it keeps going on and on and on forever. On and on and on forever. Okay? Chris, what is it in set, the domain? How do I represent that? Remember, I can't use infinities when I'm doing set. How do I represent all those numbers? Mm-hmm. And you can't forget that what in between. So x is an element of all real numbers. Okay, that's how you do it in set. That's how you do it in set. Okay. And then Kendall, what about the range? Very good. Okay. C. Those dotted lines at y equals 1 and x equals 2. What are those called? They have a name.
Oh, and
What? It's called an asymptote. Okay. It's an asymptote. You guys will learn about these last year in algebra 2 when you're doing your rational functions. Okay, rational functions have asymptotes. They are lines that the graph will get really, really close to but never cross nor touch. And that's what's exactly happening here. This graph is curving up so that it's getting really close to 1 but never touching y equals 1. And it's curving down as the x values get really, really close to 2 but never crossing or touching 2. Which means that 2 and 1 are not included in their respective domains and ranges. Okay? This is where I will always go for set to write the domain and range because it's a lot easier in my opinion. Because when you write the domain in interval notation for this, Olivia, what would it be?
Negative infinity, full parentheses, negative infinity, 2, parentheses, union, 2, comma, infinity, parentheses.
So basically it's everything except 2. 2 is not included, but you have to break it up there because there is that undefined. But in set, all I have to do is say the set of x values such that x does not equal 2. Because again, remember, it's assumed that we're talking about all real numbers, and this is so much easier than writing the interval notation. Yes? Because remember, domain is our x's. And so this graph is defined for all the x's that go from negative infinity all the way up to 2, because at 2, you have that vertical asymptote, which means the graph is either going to cross or touch, which means it cannot include 2 in the domain. Then it will pick up after 2 and continue on and on forever. So those lines, even though the arrow stops it, they're still continuing to get very, 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 very close. Like I'm talking about the x value could be 1.9999999, but it'll never, ever be 2. 2 is what makes the function define whatever it was. The range, Brock, what's the range in interval?
The range in interval?
Yep. What's the lowest the graph goes? Positive or negative? It goes to negative infinity. So it goes from negative infinity and then, yep.
1 to infinity.
And what do I need around everything? Parentheses. Or I could just say the set of y values such that y does not equal 1. And again, that's a lot easier than trying to do it with intervals and all the unions. So it's like here, okay? These are all the algebraic versions of some of these functions that you'll deal with, okay? And unfortunately, you won't always have a graph to use, but you got to use what you know about math. I don't know. You know you cannot take the square root of what types of numbers? Negative numbers. So that means that whenever you see a square root, whatever's underneath that square root always has to be greater than or equal to 0 because you cannot take the square root of a negative number. You can take the square root of 0, but you cannot take the square root of a negative number. So for example, like in A, where I asked you to state the domain of it, well, it's going to be all the x values where what's underneath the radical doesn't produce a negative number. So that's x plus 6 is greater than 0. So it's going to be all the x values that are greater than or equal to negative 6. And this is already what you need to write it in set notation. You just include the such that and the set of x, and you have your domain. Simple as that. Okay? For B, you have f, the function f such that x produces 1 over x squared. Can I plug in any and every number in for x and always get a y value back? What number could I not plug in? Why not? Because you can't divide by 0. It's undefined if you divide by 0. So anytime you have a fraction, whatever's on the bottom can never equal 0. So when you have ones that are fractions, you just set the denominator not equal to 0 and you solve it. How do I solve for x? You take the square root. What's the square root of 0? So it's all the x values except for x does not equal 0, and there's my domain. Am I doing this too fast? What about d, when you have a radical in the denominator? Both rules apply. When you have a radical in your denominator, first off, we know we cannot take the square root of what types of numbers? Negative numbers, which means it has to be greater than or equal to 0. But because it's in the denominator, it can't be 0. So that means that when you have a radical in the denominator, whatever's underneath that radical has to be greater than 0. Not equal to, because if it equals 0, it's undefined because it's in the denominator. So that one in D, whatever's in the denominator, and underneath that radical, which is just x, has to be greater than 0, and I have everything I need to write it in set notation. Sometimes you'll have to solve, it just depends on whatever it is that you're given. Sometimes you might have to factor, again, it depends on what you're given. Questions? Do C, E, and F on your desk. Anyone, what you get for C? It cannot equal negative 1. Because it's one of the ones that has just the denominator, so it cannot equal 0. Just the denominator. What about E? X cannot equal 3. Again, another denominator one, so you set the denominator not equal to 0 and you solve it. So you can either add x, subtract 3, divide by negative 1, but it's going to be x does not equal 3. What about F? X is greater than or equal to 4? Less than or equal to 4? Let's see, 4 minus x has to be, this one right here, greater than or equal to 0. How do I solve this? Subtract 4, so this gives me negative x less than or equal to negative 4. What do you have to do? And anytime you divide by a negative with the inequality, you have to remember to change the sign. So it is going to be less than or equal to 4. Questions on domains? If a function does not have one of these 3 restrictions on it, the domain is all real numbers. If it doesn't have a square root, if it doesn't have a fraction with the denominator, and it doesn't have a radical in the denominator of a fraction, it is all real numbers. It is all real numbers. Negative infinity to infinity. Okay? Composite functions. You've seen it before. The open circle. Not the closed one. The closed one means what? A little louder. It means multiplication. The open circle means composite. That means you plug one function into the other one. Okay? Don't be thrown off by the notation either. F composed of g of x. That means f of g of x. That means you're going to take the g function and plug it into the f function everywhere you see an x. So that g function, which is 1 minus x, gets plugged into the f function everywhere you see an x, like so. And then from there you simplify. When I distribute over the 2, I get 2 minus 2x plus 3. So then my answer is negative 2x plus 5. That's composite functions. Just make sure that whatever's on the inside is the function that gets plugged in, not vice versa. Okay? Because there is a difference between what you see in A and what you see in B. This time, I'm plugging F into G. So that's going to be 1 minus 2x plus 3. And be careful, you're subtracting x, which means you're subtracting that entire function, which means I'm going to have to do what to that negative? Distribute it. So that's 1 minus 2x minus 3, which is a negative 2x minus 2. As you can see, they are not equal to each other. When you actually have a number instead of the x, you can always do the composite first, then plug in negative 3 into the composite. Or you can actually plug the number into G and then take that answer and plug it into F. You still get the same answer no matter which way you do it. Okay? So I can find G of negative 3. So I plug negative 3 into G. When I do that, what do you get? 4. So then I take that answer and plug that into F. And 4 times 2 plus 3, and then that would be your final answer. It's the same thing you would get if you were to plug negative 3 into F of G of X. Okay? Here, I plug 0 into which function? F. What's F of 0? 3. Then I take that answer and plug 3 into G. What's that? And then that is your final answer. Algebraically, no problem. Right? Show me. G of G of X means I'm taking the G function, which is 5x minus 7, and I'm plugging it in back into G for everywhere you see an X. So that should have been 25x minus 35 minus 7 for 25x minus 42. Did you get that? For this one, got some different answers on some desks. If I plug 1 into G, what do you get? You get negative 2. So then you plug negative 2 into F. 2 negatives make a what? So this should have been 6 plus 2, which gave you, doesn't that simplify?
Yes.
To 2 square root of 2, because it can break down as the square root of 4 times the square root of 2. So 2 square root of 2. Yes, simplify. These other ones, F of 6 was what? 0. So then G of 0 would be, and this one, F of 2 was what? 2, because it was the square root of 4, which became 2. Then I plugged 2 back into F, and I get 2. Did I do that too fast? So I didn't show all the steps? I can. What about from the table? Just got to be able to read the table. You just got to be able to read the table. We're going to find these different values below. We have F of G of 3. That can be written like so. This table, along the top row, you have X. Along the bottom row, you have the corresponding Y's for F and the corresponding Y's for G. So you work from the inside out. G of 3. That means you go to where X is 3 and the corresponding G of X column to get 7. So G of 3 is equal to 7. From there, you find F of 7. So you go to the 7 in X and the F of X, and you see where they overlap, and your answer is negative 2. Did everybody get that? Yeah. So what you have here in this table is you have the outputs for, you have the corresponding y's whenever you plug in these respective x values for f of x and g of x. So you say you're okay when we found g of 3 to get 7? So then that means we have to now use 7 as our x value and find out when x was 7, what was f of x. And then that's how we got negative 2. Okay? Anything, the tables, in my opinion, I feel like the table's easy. You just got to make sure you know how to read it. Here, what am I going to find first? F of negative 1. So I go to negative 1 in my x column. I see where f of x was for that. And what is it? 9. So now I'm going to find g of 9. And it's going to be negative 4. Make sure you pull it from the right column. Here's 9. Then my g of x, I see where they overlap, and that's my answer. The last one, f of 9. What's f of 9? So now I'm going to find f of negative 1, which is 9. No. It won't always be that like that. Okay? It just happened to be whatever the function was that ended up producing the same value. You okay on the table?
Yes.
Sure? Have you ever seen this way before? Something new? Yay! Oh, that's listening. What about from a function? From a graph? Showing you all the different ways that you can do composite functions outside of being algebraic. Okay, so I use the table now graphically, okay? Remember, f of anything is the corresponding y value, okay? So for this one, when you find g of f of 0, you start with the inside. You need to figure out when x is 0, what is the y value on the f function? It's 0. So then you take that and you plug 0 into the g function. So when x is 0 on the g function, what's the y value? Negative 4. And then that's your final answer. Okay? So remember, the inside represents the x value, the outside represents its corresponding y value on the particular function. Okay? Let's do B to make sure you guys are good, and now I want you to try C and D before we go over the answers. Okay? So in B, you have to find f of 1 first. So when x is 1 on the f function, what's the y value? 1. Then you need to do g of 1. When x is 1 on the g function, what is it? Very good. On your desk, do C and D. What's g of negative 2? 0, because you go to the g function at negative 2 and you see that it is 0. The corresponding y value is 0. So then 0 becomes your new x, and you go to 0 on your f function, and you see that the answer is going to be 0. Make sure you use the right functions. G of 0 is negative 4. That is the corresponding y value when x is 0 on the g function. So now negative 4 becomes the x value that you're looking for the corresponding y value on your f function. Well, here's negative 4. There's the point on the f function when x is negative 4, y is, and that's how you do it with the graph. Have you ever seen the graph way done before? SAT. They like to do these. Give you a graph. Clear your desk. The last little bit to go over is inverse functions. Okay? Inverse function. A function is 1 to 1, where for each value of x, there's only one value of y, and for each value of y, there's only one value of x. That's what it means to be 1 to 1. So in other words, one-to-one functions satisfy the vertical line test and the horizontal line test. So you have your functions, and then you have the respective inverse functions. And you'll know, if anything, if an original function is going to have, or if the inverse is going to be a function, is if it passes the horizontal line test as well. That's what it means to be one-to-one. Okay? Now, if the function is one-to-one, it will have an inverse in which we denote, which I spelled incorrectly because I was rushing. Which we denote as f to the negative 1 of x. Okay? Remember that negative 1 in the exponent, that indicates inverse notation. It is very different from f of x. So if you put f of x when you're really talking about the inverse function, you do get marked off. Notation is important. Inverse functions are reflected over the line y equals x, which causes basically the points on the original function to be exchanged for the inverse function. So the most important thing to take away from this is that inverse functions are reflected over the line y equals x, which means is that if you ever are trying to look to graph the inverse function, you just take the points on the original and switch your x's and y's and plot those, and you have your inverse function. And of course, you denote it with the negative 1 in the exponent, and notation is important, so you want to make sure that you use the proper notation when you're talking about the inverse. Literally, everything is switched on the inverse function from the original function. Okay? So that means the domain of the inverse is the range of the original function. And the range of the inverse function is the domain of the original function. Literally, everything is switched. Not just the points, but the domains and ranges are as well. Algebraically, do you remember how to find an inverse function? Well, I've been harping on this whole concept of making sure that you do what with inverse functions? You switch the x's and y's. So if you're ever given a function, the first thing you want to do if you're trying to find the equation of the inverse is switch your x's and y's. And then from there, you want to solve for y. So you want to make sure that you switch your x and y. You want to make sure that you solve for y. And because y technically indicates the original function, you want to always make sure that you include your proper notation once you've actually gotten y by itself. That's algebraically how you find an inverse function. Okay? And something like this, remember, if you have an inverse, that means there's one x for every y, and every y has one x. Is A that way? Does A have an inverse? Yes, it does. Its inverse is going to end up being what? 2, 1, 4, 2, 5, 3. Because again, all you do is switch your x's and y's. Okay? Algebraically, if you're given two functions, this is just one that you can, I'll do the video separate so then that way you can see it. It's just applying the inverse in a little different of a way. I'll go back and do that. Algebraically, if I wanted to find the inverse of this function, where is the y in this? That whole thing. That's the y. So that becomes x, and you switch your x's and your y's, and you solve for y. Okay, so you switched x and y, and so you need to solve for y at this point. Since you do have a denominator where y equals y minus 3, to get that out of the denominator, you want to multiply both sides by y minus 3. So when you multiply both sides by y minus 3, you'll end up getting x times y minus 3 equals 3y minus 8. Now, as you can see, you have y's on both sides of your equation, and that's not what you want. You want to make sure that all of your y's are on the same side. So you want to go ahead and distribute that x over to get xy minus 3x equals 3y minus 8. Once that's done, again, your y's are still not on the same side, so you want to go ahead and get all your y's on one side and everything else on the other side. So I'm going to add 3x to both sides, and I'm going to subtract 3y to both sides. And what that will give me is xy minus 3y is equal to negative 8 plus 3x. Now your y's are all on the same side, which means that I can factor out a y. And the reason why I want to factor out a y is because I'm trying to get it by itself. And since both of these terms on the left side have y in common, I can factor that out, which allows me to divide both sides by x minus 3. And that is my inverse. So then I just go back through, put in the proper notation, and negative 8 plus 3x all over x minus 3 is the inverse of this function. Now, if you're like, wow, that's a lot, Ms. Anderson, well, these are the hardest of the hard type of problems. All the other ones are very simple. Just switch x and y, solve for y, and it's pretty much basic algebraic properties from there. Here's a simple example of finding the inverse of g. G to the negative 1 of x is asking to find the inverse of this function right here. So you want to go ahead and switch your x's and y's. So then you'll have x equals 8 minus y over 2. And to solve for y, this one's a lot simpler than the last example because you only have one y. It is in the numerator of the fraction. So then you just multiply both sides by 2 to get 2x equals 8 minus y. Subtract 8 from both sides. And then divide everything by negative 1 to get y by itself. So that gives you negative 2x plus 8 equals y. But we don't write y. We actually write the proper inverse notation to indicate that it is an inverse. All right, let's look at B. B says g of x is equal to negative 1. So since g of x is equal to negative 1, we're going to actually set the original g function equal to negative 1 and solve for x. So we're going to multiply both sides by 2 to get x by itself. Negative 1 times 2 is 2. We're going to subtract 8 from both sides. Negative x is equal to negative 6. Divide both sides by negative 1 and x equals 6. In C it says to show that f to the negative 1 of negative 3 minus g to the negative 1 of 6 is equal to 0. In show problems, you want to make sure that you actually show all of your work. That's where you get the points from. So I'm going to go ahead and use the fact that I already have the inverse of g to the negative 1 of x. And I'm going to actually find the inverse of f, so then that way I can plug in negative 3 to show that the difference between the two is 0. So I need to switch my x's and my y's on my f function, and that was 2y plus 5. Then solve for y by subtracting 5. Then dividing both sides by 2. And then this is the inverse of f. And so then I'm going to plug in through negative 3 into the inverse, and then plug in 6 into the inverse of g to show that it does indeed equal 0. When I plug in negative 3, that gives me negative 3 minus 5 over 2 minus negative 2 times 6 plus 8. And don't skip any steps because you do not know what the grader is actually looking for in the actual math that you're doing when you're solving this problem. So I'm going to multiply the negative 2 and the 6. Then I'm going to divide negative 8 divided by 2 is negative 4 minus the sum of negative 12 and positive 8 is a negative 4. 2 negatives make a positive, and this does indeed equal 0. And for the last part of this particular problem, we're trying to find x such that f of g to the negative 1 of x is equal to 9. So that means that we're actually going to have to take the inverse function, plug it into the f function, and then solve for x. So the inverse function, again, is right here. We're going to plug negative 2x plus 8 into every x we see in the f function. And we're going to set that equal to 9 and solve for x. So we're going to distribute over the 2. Combine like terms. Subtract over that 21. 9 minus 21 is a negative 12. Then divide both sides by negative 4, and x is equal to 3. So when x is 3, that is what makes the composite between f and the inverse of g equal to 9. And these are just a few problems where inverses are involved along with any of the other types of functions that we dealt with today in class.